I'm set up here. It's always fun to start off with a synthesis problem at 8 o'clock on a Monday morning. So the first thing I noticed about this problem, we're starting with 1-butene. So this is just plain old 1-butene. And then we're making a compound where we have 6 carbons, and this is Cis3 Hexine. So Cis3 Hexine. So not only is, are we changing the carbon skeleton, right? We're starting with 4 carbons, and we're ending up with 6 carbons, but it's a cis alkene. So we know that we're going to have to do a hydrogenation to produce a cis alkene. Well, if you think about ways to increase the number of carbons in your carbon skeleton in this class, we don't have that many ways. Later on, we're going to learn more and more ways to increase the number of carbons in a skeleton, especially in organic chemistry too, but that's not what we're studying right now. So let's think about ways that we can increase the number of carbons. And really, the only way that we've got would be to have 1-butene. If we had 1-butene, which has 4 carbons, right, we could treat that with sodium amide followed by ethyl iodide, right? That's really the only thing that we've got. So in the first step, we treat it with sodium amide, and I don't want to get my step numbers mixed up here. Sodium amide, and then we'd have to treat it with ethyl iodide after, and then we could do a hydrogenation using Lindlar's catalyst to make the cis alkene. Well, then the question becomes, how do I get from 1-butene to 1-butene? Right now, if you're unsure, if you're struggling and you're saying, well, I'm not sure exactly how to do that. Well, what you could do is kind of take a step backwards, because the good news is that in Organic Chemistry 1, you kind of only have a few ways of, or oftentimes only one way of making certain compounds. So in order for us to make this triple bond, we know that since we're starting with 4 carbons here and we're ending up with 4 carbons there, we know that we would have to start with some kind of dihalide, right? 1, 2, 3, 4 carbons, and we'd have to start with a dihalide like this, and then we could treat that with excess sodium amide to do the double elimination and deprotonation, followed by treatment with water. Right? We know that we can do that, so then the question becomes much more manageable when we say, well, how could we get from here to here? Because that's just a bromination reaction. Right? So what we're going to do is we're going to take our 1-butene and we're just going to treat it with bromine. We're only going to form one stereocenter, but I'm just going to leave it out because I'm not going to draw it as a dash or a wedge or anything like that, because we're going to eliminate that stereocenter anyway. So there you go. We end up with our vicinal dibromide. Now we're going to do that double elimination. Right? First, we're going to treat it with excess sodium amide. And we did this many times last class. That does the double elimination. If you were to just treat it with excess sodium amide and leave out the water, you end up with a carbanion, right? You end up with this alkynide. But we know that in the second step, we treat that with water, and that adds the terminal proton here, right? Okay, well, now what we've got to do is we've got to add our 2 carbons to our molecule. So first, we're going to treat that with, again, sodium amide, which is going to do the deprotonation. And then we're going to treat it with ethyl iodide. So I'll put ethyl. And if you chose ethyl bromide, that's fine. If you chose ethyl chloride, that's fine too, whatever. But that gives us our 6 carbon molecule. So this would be 3 hexine, right? This is 3 hexine, okay? And then all we have to do is reduce that to make the cis alkene. So we're going to take that and we're going to treat it with hydrogen and Lindlar's catalyst, which is that poison catalyst. And again, I told you, if you were to Google that or research the Lindlar's catalyst, you see that it varies from time to time what is added to the palladium there. Anyhow, there is one more kind of aside here, and I'm not sure if the textbook brings this up or not, but there is one shortcut that you could use in this synthesis, in my opinion, to speed it up a little bit. And it's to go from here, from the vicinal dibromide to the 3 hexine. You can actually do kind of an end run around this, because if you treat this with excess sodium amide, okay, come on, there you go. Like I told you, what you actually end up with is the alkynide ion. And since you have the alkynide, all you'd have to do is to treat it with ethyl iodide or ethyl bromide. We'll just use ethyl bromide again. So you would be able to skip this step and this step. You don't have to do the adding of water and then another equivalent of sodium amide. You could leave that out entirely. Now, this is one of those cases where I'm not going to be splitting hairs and say, oh, you did this, that's no good. No, it's no problem with that. But, it is kind of a shortcut, which, organic chemists are just like everybody else. We're always looking for the easiest way to do something, work smarter, not harder, right? So I would say that would be kind of a shortcut there. You could speed it up by a couple of steps. All right, let's move on to B. We have an aldehyde. We don't have many ways of making an aldehyde in organic chemistry 1, except for in terms of retrosynthesis, if we had 1-butyne, right, because we have 1, 2, 3, 4 carbons in this molecule, we know that we could do an anti-Markovnikov addition of water to this, which would produce an enol, which would tautomerize to give us the aldehyde, right? That's just one of the reactions that we learn in this chapter using the hindered borane. And if you don't remember it, let's cover it. So the first thing we need to do is go from 1-butene to 1-butyne. We did that in the last problem, so let's do it again, right? Practice makes perfect. Just repeating the same old conditions will not be deleterious to your health. So we have our vicinal dibromide. We're going to treat that with excess sodium amide, and then we're going to treat that with water, and that is going to make 1-butyne like this. So then what we're going to do is we're going to treat this with the hindered borane. If you want to write 9-BBN, which is not BBN, yeah, BBN, there we go. Or if you want to write the hindered borane like this, I noticed that the textbook does it this way quite a bit, where he just puts 2 R groups and then BH like that. It just tells you it's a hindered borane. It could be 9-BBN, it could be dicyanyl borane. There are probably others on the market that I'm not even aware of. Okay, and then the next step, we're going to treat that with hydrogen peroxide, followed by sodium hydroxide. And what that's going to do is that's going to do an anti-Markovnikov addition of water. If you look at our alkyne, we have the carbon in red and the carbon in blue. Well, if it's Markovnikov addition, that would mean that this carbon would take the hydrogen, but this is anti-Markovnikov addition, so that carbon in blue is the one that's going to take the hydroxyl. So we end up with this compound. Let's draw it out just for interest's sake. We end up with this, where we added the proton here and we added the hydroxyl here. So what we end up with is an enol, right? And when you have this kind of enol, it's going to undergo tautomerization, which is just the rearrangement of the molecule. It's the movement of a proton, the hydrogen atom, and a double bond, and we end up with an aldehyde like that. There you go. So again, it's one of those problems where if you were stuck, let's say you're practicing at home or you're on a quiz and you're like, I don't know, I'm not sure. You think about it, how many ways do I have to make an aldehyde? I've got ozonolysis of an alkene. Sure, you can make an aldehyde that way, but the problem is you wouldn't use it here because you're starting out with 4 carbons and you're ending up with 4 carbons. So you wouldn't want to change, the carbon skeleton in any way. So then really all you've got is the anti-Markovnikov addition of water to produce the enol across that triple bond. Okay, and the last one that I want to look at in 9.29, we already did D, E, and F last class, is to go from 1-butyne to 2-butanol. I know we haven't done alcohol nomenclature. It's not covered in this class, but this is called 2-butanol. It's the name. All is a suffix that we use for alcohols, and it's on the second carbon like that. But the first molecule, you know how to name that. This is 1-butyne, a little kind of ubiquitous this morning, I guess, just showing up in everything. Anyhow, we have 1-butyne and we want to make 2-butanol. Well, this is another case where I would think about this in terms of retrosynthesis and just say, well, look, if I want to make this secondary alcohol, the easiest way to do it would be to start with 1-butene and then just do a Markovnikov addition, right, of water. So just treat it with dilute acid and you're done. So then the question becomes the same old thing that we've seen already, except in reverse, because before we were always starting with 1-butene and making 1-butyne. Now we want to go from 1-butyne to 1-butene, which is actually much simpler because all we have to do is reduce the triple bond to a double bond. And for that, we got a couple of options. You could either use hydrogen and Lindlar's catalyst. That will work. So we could treat this with H2 and Lindlar's catalyst. But since there's no cis or trans on a terminal alkene, you could use sodium metal reduction if that's what you like. So NH3 liquid, either one will work. They're both totally fine. Either way, you're going to end up with the same molecule, which is 1-butene, and then we're just going to treat that with our dilute aqueous acid. We do a Markov-Nikov addition of water, and that's it. We're done, just like that. All right, I think these are all very reasonable synthesis problems. Not simple, but reasonable, and they are a great way to practice all the reactions that we learn in this chapter. So I want to turn our attention to question 9.37 quickly. I don't want to spend too much time on this problem, but I thought it was a really good one. You know, these are the kind of problems that I recommend tackling. It really can help you, what's the word I'm looking for? Solidify, you know, your alkyne chemistry prowess. So we're starting it with this molecule, and we just want to do a bunch of different transformations. So this would be 1,2,3-methyl 1-butyne is the name of this molecule. And let's say we want to take this and we just want to go and we want to make this compound here. Could anybody tell me this reaction that's going on here, is this a Markov-Nikov or an anti-Markov-Nikov addition? What's going on here? And I'm not trying to fool you or anything. It's just a Monday morning kind of question. What would you consider this, a Markov-Nikov or an anti-Markov-Nikov addition? Absolutely, yes, yes. So Allison, yes, it's a Markov-Nikov addition, right? Because the rich are getting richer, right? If we think about it like this, I've got one hydrogen on this carbon, but I have no hydrogens on this carbon. So now this carbon is getting another proton, right? Whereas this carbon is gaining the chlorine. So this is a Markov-Nikov addition of HCl across the triple bond. So a Markov-Nikov addition, let me just scribble that in here. So this would be a Markov-Nikov addition. And the way that we would do that is we would just treat the molecule with HCl. So HCl, and I like to specify, since you're only adding one molecule of the HCl, you could just write one equivalent, okay? And all that means is if you had 1 mole of this, you would add 1 mole of that. That's what equivalence means. It's nothing fancy, okay? Not meant to be anything mind-boggling. Let's go to the next one, and I think this is one that everybody would nail right away, probably faster than me. We're going from the alkyne to the alkene. So we just saw this. We've got a couple of options. You can do hydrogenation with Lindlar's catalyst, or you could use sodium metal reduction. I'm just going to write in hydrogenation, which seems to be the favorite of the author. And the reason why is, like I told you last class, there's nothing wrong with these conditions. Sodium and liquid ammonia. The only problem, and I'm being cheeky here, is that you're messing around with sodium and liquid ammonia, both of which are nasty, right? Sodium metal is dangerous, and liquid ammonia is kind of a pain in the neck to work with too. Whereas hydrogen, you can just put that in a party balloon, and Lindlar's catalyst is just a solid. You can weigh it. You have to be careful with it, but still, you just weigh it out. Okay, I have a question for you guys. Could anybody tell me, you know, what I would do to do this transformation here, to go from the terminal alkyne to this nice carboxylic acid? You can give me like any hint or any clue. What do you think would be the best way to do this reaction to make this carboxylic acid? Yeah, absolutely. Absolutely. Yep. It would be to use ozonolysis, right? And the clue here that it's ozonolysis is we're starting it with 1, 2, 3, 4, 5 carbons. So we've got 5 carbons in the first molecule, but we've only got 4 carbons in this molecule. So we're losing a carbon, right? What we're doing is essentially excising a carbon from the molecule would be the term that we would use. So you would treat this with ozone, right? This is an ozonolysis, or an oxidative cleavage, as the book calls it a lot of times, followed by treatment with water, right? So not only would you get the carboxylic acid, you would also produce CO2. So since it's a terminal alkyne, you end up with CO2, but that's how you would do this one, okay? The next one, we want to make a methyl ketone. This is a real chestnut in organic chemistry. It's taking an alkyne and making a methyl ketone. So let me try to draw it as neatly as I can. And they even write out CH3 just to show you that it's the methyl ketone. And like Warren says, in this one, you'd want to go through the enol, right? So this would be a Markov-Nikov addition of water across that triple bond. So in that case, you would need sulfuric acid and water, just like, you know, the Markovnikov addition of water across a double bond. However, now with the triple bond, you need to spruce it up, right? You need mercuric sulfate, mercury 2 sulfate, which actually doesn't produce the methyl ketone right away. You end up with this compound, right? You end up with this enol, but then that enol undergoes tautomerization to give you the methyl ketone. Excellent. The next one's in a similar vein, right? Just practicing all of our reactions here. So we want to take this compound and we want to make this aldehyde. Okay, look, we're still not changing the carbon skeleton. We have 5 carbons here, 1, 2, 3. We have 5 carbons here. So no changes to the carbon skeleton. But now you can see that we're doing that anti-Markovnikov addition, right? Remember, if you're making an aldehyde, except for ozonolysis of an alkene, you've only got one other option, and that is to treat it with a hindered borane, like 9-BBN. I'm going to write that this time, 9-BBN. And then in the second step, we'll use hydrogen peroxide and sodium hydroxide. And there you go. And that would produce this enol. Let me scribble it down here. So we'd end up with this enol. And that enol is going to undergo tautomerization to give us the aldehyde. Well, I can see I kind of painted myself into a corner here. I don't have a lot of space, but let's see. The next one, we want to make a Geminal Dibromide. So we want to add, you know, bromine, 2 bromines here. This is like a double Markovnikov addition of HBr across the triple bond. So you would just use, I would just use excess HBr to do that. And then the last one is another one I think everybody would get, you know, very quickly. And that's taking the alkene and just taking it all the way, reducing it all the way to an alkane. And for that, we would just use hydrogen. And we'll choose platinum as our catalyst. And there you go. So these kind of questions, again, this is question 9.37, comes right from your textbook. I think these, he always has a question or two like these in the textbook, and I think they're great ways to practice all of your reactions, besides just staring at, you know, a sheet of paper and trying to commit them all to memory, and there's nothing wrong with that too. Let's take a look at question 9.41. I want to take a quick peek at a couple of problems there that I think are pretty good. And I'm sure that some of you did this problem already this weekend, but I think it's a good one to kind of go over quickly. I always find that questions where you're given the reagents are usually a little faster for students than ones where you're supposed to provide the reagents. But first we want to treat this with excess sodium amide. Then we're going to treat it with ethyl chloride. So ethyl chloride. And then the next thing we're going to do is we're going to treat it with hydrogen and Lindlar's catalyst. Okay. Well, after the first step, right after step number 1, you're going to end up with the alkynide, right? You would end up with this, okay, or you have the alkynide like that. But then you throw in some ethyl chloride, and that acts as a electrophile, and so that's just going to do an SN2 reaction like this, and you're just going to add an ethyl group to the end. So let's draw that ethyl group in. So make sure to count your carbons carefully, 1, 2, like that. And then we treat that with Lindlar's catalyst and hydrogen, so we'd reduce that to the cis alkene. So I need to delete some carbons here, don't I, to fix this up. So we have 1, 2, 3, 4. There we go. So there's our cis alkene, and I'll put the 2 hydrogens in here to show you that it's a cis alkene. I want to explain one thing to you really quickly here, which is the whole idea of ethyl chloride. So one thing you've probably noticed is that, and I've said this to you many times, sometimes we'll use, let's say you wanted to add an ethyl group. Sometimes you add ethyl iodide, sometimes you add ethyl bromide, and sometimes you add ethyl chloride, okay? And you're like, why can I use, you know, why can I just pick whatever I want in terms of an alkyl halide? You can't use ethyl fluoride because fluoride is the conjugate base of a weak acid, so it's not a good leaving group. Well, first of all of these are good leaving groups, right? Chloride, bromide, iodide, they're all good leaving groups, but iodide is going to be the best leaving group, isn't it? Okay, so if you're a synthetic chemist and you're in a lab, you would always pick iodide if you can. The problem with iodides is that they're pretty expensive, okay? Like the Yelp review, you know, they're you put the dollar signs by it, right? So the problem with iodides is that they're just expensive. If you buy them from a chemical supplier, they cost a lot of money. In terms of reactivity, bromide is a very, very close second place. Okay, it's a very close second place, and it's considerably cheaper. So usually, again, if you have this in abundance, you would always go for what is going to work best, right? So you would usually pick that. But if you don't have that kind of dough, and let's say you have all you have is the bromide, it's going to work pretty darn well. Okay, chloride is kind of like the loser. Okay, now before. Chloride is super cheap. It's definitely the cheapest of all three. However, usually when chemists use chloride, there are cases where it probably works really, really, really well. But oftentimes, like let's say you buy a prescription drug and they had to do an alkylation, I'm pretty sure that whenever you buy, a prescription drug, that they would use a chloride because it's so cheap. However, what they have to do a lot of the times is they'll have to fine tune the reactions very carefully in order to get a really high yield with the chloride. It can be done, but if you don't have a lot of time, I would always reach for one of these. So that's, if you've been wondering, what's the difference between all these, that's it in a nutshell. Okay. So there you go. That's what, but again, that you can use any one of the halides as a leaving group and it would be totally fine with this guy. Okay. They're all totally fine. All right, let's try the next one. This is a real classic question in organic chemistry 1. You start with acetylene, right? So we're just starting with acetylene gas. We're treating it with sodium amide, okay? Then we're going to treat it with what? Methyl iodide. Well, let's draw the intermediate that's formed. You're just going to put a methyl group on it. So you end up with propyne, and then we're going to treat it with, sorry, I wasn't reading here very carefully. We're going to treat it with the hindered borane, followed by hydrogen peroxide, and sodium hydroxide. That's going to do an anti-Markov-Nikov addition of water. So look, we've got 1, 2, 3 carbons. We put our hydroxyl here. This is an enol, which is going to undergo tautomerization to give us this aldehyde. So this is called propionaldehyde or propanal. Either name is acceptable. And if you're like, oh, good gravy. Well, that's something that's covered in organic chemistry too, so don't stress about the nomenclature of an aldehyde today. Next is, we're doing something very similar. We're going to take acetylene and we're going to treat it with sodium amide followed by ethyl iodide this time. So I'll copy this and I'll paste it here, but then I'll have to modify it, won't I? So let's delete the ethyl. Let's replace it, or sorry, the methyl. We'll replace it with an ethyl and we'll add a carbon there. And then we treat that with what? Mercuric sulfate. So mercury 2 sulfate, sulfuric acid, water, and that does a Markov-Nikov addition of water across the triple bond. That gives you this enol, which is going to undergo tautomerization to produce what? A methyl ketone. So let's draw that methyl ketone like that. And it seems like the book, he likes to draw the methyl in explicitly like that, just so you recognize it's a methyl ketone. And again, there's nothing wrong with that. Well, let's try one more. Let's try 9.41D. So again, this is 9.41D. We're taking, what's our starting material? Acetylene again. That's not very pretty, is it? We're going to treat it with what? Sodium amide. Doesn't say anything about excess. Then we treat it with methyl iodide. We saw this already. We end up with propyne. Make sure to draw this as a linear bond. You don't do, you don't do that. That's incorrect. That's not the proper way because this carbon is sp hybridized, so the geometry is linear. And then we've got 3 steps, or 4, sorry, a total of 5 steps. So the next 2 are first treating it with sodium amide, then with, ethyl iodide. Yes, ethyl iodide. So we end up with this molecule. Okay, and you can see I kind of flipped my alkyl groups. If you want to draw them this way, that's totally fine. So this is 2-pentyne, and then the last thing we do is we treat it with sodium metal reduction. So sodium and liquid ammonia, like that, and we end up with, there we go. We end up with trans 2-pentene. So trans 2-pentene. Or if you want to call it E2-pentene, that would be a proper name as well. But there you have it, folks. That covers pretty much, most of the reactions that we covered. I might have missed one or something, but that covers the vast majority of what we looked at in Chapter 9. So that's the Alkynes chapter in a nutshell. And again, I recommend trying all the problems that I posted as suggested practice problems, which can be found on Canvas.